Hello everyone, thank you for joining today. My name is Milam and today we're going to be looking at motion. So it does look like we have a lot to cover, but believe me, we're going to get through it quite quickly because these are concepts that you've been thinking about and been exposed to a lot, but now we're going to consolidate and all put it together. So we're going to define and understand how velocity, speed, distance, displacement, and acceleration are all linked together in a straight line and in a circle. So if you're ready, let's get right into it. Now, let's start having a look at how all these quantities change in a straight line, or I should say straight lines, because I'm going to be traveling my path here from A to B. Okay, so I have to go here, this way, and then up, and there, down, and all the way there to B. Okay, so we're going to have a look at how velocity, speed, distance, and displacement change with this. Okay, now, first of all, straight away, we need to remember that all sorts of physical quantities in physics fall under one of two categories, a scalar and a vector. Okay, so let's first label all of our scalar and vector quantities here. Now, velocity, this is speed with direction. Okay, so what does that tell us? Well, that tells us that it has a magnitude, which is the speed, right? How fast are we going? And then it also has direction. Okay, so what direction am I pointed in and how fast am I going in that direction? So this means that this is a vector quantity. Okay, now my speed, well, that's just how fast I'm going, okay, and that's represented by speed is equal to distance over time. Now we're going to look at the velocity equation as well, so hold on to this. Speed is equal to distance over time, right? So how much distance am I covering in a space of time? Okay, so this is only magnitude, right? How fast am I going? And then, so this is a scalar. Okay, so now, how can we develop the velocity equation? Well, actually, first let's have a look at distance and displacement, then we'll develop the equation, that's easier. Okay, so my distance, so that's just how far have I gone, how far. Okay, and there's no distance equation, it's just a physical quantity that we can measure. It's measured in meters now. This is just how far I've gone, so this is just a magnitude. And so if this is just a magnitude, it's only a scalar, all right? Because we're looking at what's the scale of my movement, okay? So now we have displacement. So this is how far and where, okay? So what direction have I gone? Now, so this is magnitude, right? How far and direction. And so this is a vector quantity. Vector, ooh, I'm going over my path. Oh well, okay. So now let's have a look at how we can construct a velocity equation. Well, we know that velocity is a speed with direction. Okay, so we know that it's going to follow the general formula, right? So velocity is going to equal some kind of distance over a time. Okay, time is constant, it's a scalar. Well, it could be a scalar and a vector, but that's a very different question and we don't need to worry about it. But we're going to assume that's a scalar right now. Now, are we just going to use any old distance? Well, no, because remember we have velocity is speed where, so speed with a direction. So instead of distance, we use displacement, which is given the quite confusing symbol s, right? So velocity is the displacement over time. Now, so we understand the velocity equation now. Now let's have a look at how all of our and I've missed one here as well, actually, acceleration, but we're going to have a look at all of that after we plot down on our path where all these physical quantities are actually happening. So if I was saying let's have a look at the easier one first, which is distance and displacement. Now, the distance from A to B, distance A to B is equal to this path right here. Okay, let's do it in a dashed line. Okay, so I have to go up and down and around to get to B. Okay, so that's my distance. So let's just say dashed line. Now, what's my displacement? Displacement A to B. Wow, that is a distance with a direction. Now, really, I'm just getting from A to B, right? So what I do is I take the straight line route from one point to another, so from A to B. So my displacement is just this. right there. So that's that straight line right there. So that's my displacement, and my distance is or following the actual path itself. Now by this you can sort of realize that, oh yeah, distance can actually be greater than my displacement. So because my my distance takes me around the path, whereas my displacement just goes right through it. Okay, so now if we were to look at say I had my stick person, right? Oops, deformed head for my stick person. Now my stick person's speed could really just be calculated by how fast he can do this entire path right here. Okay, so that's his speed, but his velocity will be demonstrated by how fast he can do that first path on A right there, then how fast he can do this upwards path there, then how fast he can do this, how fast he can do this, how fast he can do this, and then I take the average of all of those velocities to get average velocity, right? But that average velocity turns into speed, because as soon as I average all of these individual components, this way up, this way down, this way, I get a general understanding of my person's speed, but I lose the understanding of direction. So we can look at average velocity is equal to speed. Now I've just told you that my stick person his velocity goes this way and then this way. What changes the direction of his velocity? Well, that's another quantity called acceleration. So let's do that right there. Acceleration. So this is the change in velocity. Now, when a lot of people think about a change in velocity, they always jump to, speeding up or slowing down. But we don't always have to speed up or slow down to have an acceleration. An acceleration is really usually just used to change the direction of our velocity. So this has a magnitude and a direction. I'm not going to write all that because I'm running out of space, but I'm just going to skip straight to that it's a vector and it has an equation. So actually I'll write it right here just so it's easier. So acceleration, which is given the symbol a, is equal to v minus u over, actually I can do that just to tell you that the first one's a v and the next one's a u, over t, so time taken. Okay, so let's tell you what v and minus u are. So v is our final velocity and u is the initial velocity. Because remember, our acceleration is talking about the change in velocity, so final minus initial, that gives us our change. Now, over time is what everything is, so it's the change in velocity over time, so that gives us acceleration. So we know that velocity is measured in meters per second, time in second, so what our unit ends up being meters per second, or meters per second squared. Okay, so that's our unit for acceleration, which is the change in velocity. So at this corner right here, I have an acceleration because although my actual speed, how fast I'm going, might not change, my direction does, and so there's an acceleration there. There is also an acceleration at this corner here, and at this corner here, and at this corner here, before I end up going the home stretch to B. Okay, so that was a lot of information right there, but now you should be able to understand how velocity, speed, distance, and displacement are linked in a straight line. Okay, so now let's understand motion in a circle. So I have here my circle, right, and I have a few arrows labeled on it. Now, this arrow right here shows you direction of motion. So we can see that our point here, right, is traveling anti-clockwise. Okay, so that doesn't really mean anything. It's just there to give you some sort of visual representation. Okay, so just imagine this particle spinning this way, right, anti-clockwise. Now, our black arrow right here represents its velocity. And now let's think about this, right? We understand that velocity has is speed with a direction. Okay, so we can see that our particle wants to go forward. So now, what is it that actually turns the force? Sorry, it turns my particle. What is it that means that at the exact next moment when my particle is over here, right, the velocity changes to this? Okay, what's actually doing the changing in velocity? Well, that would be this green force right here. This is a resultant force. Okay, so this force is a resultant. So I'm just going to put a bigger R and do a dot. Okay, so this resultant force right here is always acting 90 degrees to the velocity of my particle. Now, because it's 90 degrees, it doesn't actually speed up or slow down my particle, it just changes its direction. Now, how does it actually do this? Well, this sort of force has a very special name, and this is called a centripetal force. Okay, centripetal comes from the Greek word centripete, which means center seeking. Okay, so we always have a center seeking force which is 90 degrees to my object's velocity, right? And it's always looking at the middle, the center of the the center of the circle that I'm traveling in. Okay, now, okay, we have the centripetal force. Why do we care? Well, this centripetal force provides an acceleration to our particle. Provides an acceleration. Okay, hint, hint. This acceleration is called centripetal acceleration. Now, whenever we hear about acceleration, right, our mind instantly jumps to speeding up or slowing down. But remember that I told you that because this force is at 90 degrees to our particle, it doesn't actually speed up or slow down at all. So all the acceleration does is change the direction of the velocity. Changes the direction of velocity at every instant. Because remember, if we move the particle forward a bit, to over here, to over here, to over here, right? It's changing the velocity bit by bit at all of those instantaneous points. Okay, change the velocity at every point. And now this acceleration is what actually changes my velocity to allow my particle to travel in a circle. Now, what are some factors that can affect this centripetal center seeking force? Well, we have a few. Our first one is mass of an object. If the mass of the object increases, my FC, so I can do FC, right? Force centripetal also increases. Now, if my velocity of my object increases, so how fast I'm traveling around in the circle, velocity increases. Velocity increases. My centrifugal force also increases by a factor of 2, so it gets squared. Okay, but you don't really need to know the exact values of this and sort of like the exact relationships, because there's actually a very elegant equation that does all this, but you don't need to know that GCSE, only when you get to A level. So, but for now, all you need to understand is that when the mass of the object increases, or the velocity that the object needs to travel around in that circle increases as well, the centripetal force also needs to increase. Okay, now, another thing that we can look at is the radius. How big is the actual circle that I'm traveling? So my radius will be over here, right? Half the distance from across the circle, right? Half the diameter. Now, what we need to understand is that the radius and the centripetal force required to allow my particle to travel in that circular path is inversely proportional. So if my radius decreases, so I get a smaller circle, the centripetal force required to keep me going in that circle increases, right? So they move in opposite directions. And this is often demonstrated when you're doing an experiment in a lab, right? Where you have a string, where you have a stick and attached to it is a string, and at the end of the string is a mass. And so when you spin it around, you can see that with the same sort of force, how the velocity of the spinning mass changes over time. So you might be able to do that at school, but for now you understand centripetal force and the motions of an object in a circle.